Okay, Bismillahirrahmanirrahim. Any questions before we start? आज लोग सारे ईद बनाने चलेंगे. Okay, so I have homework 1 was due yesterday, so that's submitted, and I've just posted the homework 2. Okay, so maybe if you want, at the end of the class we can just spend 5-10 minutes just go over the homework, so you know how to proceed with it. Okay, like I announced, there will not be a class on Tuesday. We'll meet on Wednesday and Thursday, and then inshallah after that we won't have a makeup class on Saturday, and then the week after that we'll just proceed regularly. There's no quiz today. Instead, the quiz will be on Wednesday, inshallah. Okay. All right. So where were we? We were talking about pinhole cameras. That's what we developed yesterday. We know that the pinhole camera in canonical view can be written like this matrix. Except I've written it in real image coordinates. I should write it, if I want to write it in pixel coordinates, there will be an mx and an my here. I can do that. I got a pen now. Oops. How do I get a pen in this? Okay, forget it. Okay, so there will be an mx and an my here, and this will be x0 and y0. If I want to get it into pixel coordinates, I have to scale according to pixel coordinates. Okay, so that's your canonical view, and this is your general view. In general view, you have an additional transform here. This rotation is no longer identity, and this translation is also no longer identity. Yeah.
Can you explain again why a principal point needs to be centered? You said the principal point needs to be the center of the image. I'm confused as to what the center of the image is and what that means.
No, the principal point, so the question is, why is the principal point at the center? So by definition, the principal point is the point where the optical axis or the principal ray cuts the imaging plane. So that is by definition the principal point. Now, if the pinhole is at the center of the camera and the film is vertical, which is what the central projection is, we are not talking about oblique projections. In oblique projections, the angle of the film could be different, but we are not talking about those. So in this case, and if I take it symmetric around that optical axis, then the optical axis will cut it at the center. So now in typical camera constructions, it's close to center because there is some error, because these pixel dimensions are in micrometers, so there is some error of the assembly, but it's typically close to center. Okay, now the image origin does not have to be the same as the principal point. Therefore, we added the principal point offset from whatever the image origin is. Okay, but the principal point is a point defined by optical properties of the camera. Does that answer your question?
What is the image origin?
The image origin is wherever you take your pixel 0, 0.
Is it going to be what the word origin is mapped onto?
No, not necessarily at all. The image origin is, if we are working in pixel entities, the image origin is a pixel quantity. In fact, you are already familiar with it even before we started talking about cameras, because your matrix has an origin, right? Okay, so here we can write this more compactly as x is equal to k r t r pipe t x, or as k r I pipe minus c x. Okay, so that's the way to write the camera model, and I described all the terms here last time. Small x is the image point, cap x is the world point, k is a 3x3 matrix of internal camera parameters, which includes focal length, mx, my, principal point, offset. R pipe t is the 3x4 matrix of external camera parameters. We call k intrinsic matrix and R pipe t the extrinsic matrix. Okay, R is the rotation needed to align the camera to the world axis, because the original one going from the origin to the camera was R transpose, so R is the reverse of that. So the rotation needed to align the camera with the world axis, and T is the translation needed to get here, which is really equal to minus R pipe C if you multiply these matrices together the way we derived them. Okay, yeah. Which one? This one? Yes. Yes. So this part is R, this is T, which is what I wrote more compactly as R pipe T. Okay. So this equation and this equation are exactly the same. It's just the way you arrange it. Okay. So I'll give you an example. That's what we did last time. I'll give you an example of how we use the camera model. Okay. So we want to how we set up the camera model. So I want to set up a camera model for this scenario, which is a typical surveillance system scenario. A typical surveillance camera, which you see mounted on walls or roofs and so on, has two allowed rotations. We call this pan and we call this tilt. Okay, and it's fixed. So it's fixed such that it can rotate about. There's a gimbal, which is like a ball and socket joint type of thing. So on that gimbal, it can pan, it can tilt, but it really can't do this. So it cannot roll. Okay, so that's a typical surveillance camera. So I'm just giving this as an example, even though what I've said is complete on the previous slide, but I'm just giving it an example. I want to use it for this type of camera. So how will I set this up? I will think that the camera was originally at the origin, right here. Okay, the camera was originally at the origin, pointed that way, pointed along the z-axis. Okay, so it was like that, looking upwards, because that's the canonical view. Okay, now it was translated by first some R1, R2, R3, because originally this point, the center of the image, or the pinhole really, that was at the origin. Okay, but between that point and where it can actually rotate is an offset, and I'm calling that R. Okay, so when I want to rotate the camera, I first have to bring the physical point of rotation onto origin, because rotation will happen about the origin when I set up a matrix. Okay, so the camera was then translated to R1, R2, R3, so that the gimbal is at the origin. Okay, and then it was rotated by phi along x and theta along z. Those are the two pan and tilt rotations. I need two matrices to describe that. And then it was translated, this big translation in the world, x0, y0, z0. So wherever it is in the world relative to the world coordinates. Okay. So notice what I'm doing. I'm assuming that the camera was in the canonical view, and then I am shifting it, rotating, translating, which are all rigid body transforms. So I'm doing rigid three-dimensional rigid body transforms to get the camera to where it is actually in the world, and that will help me set up the camera model. And to get it there, I have to do these measurements. I have to know what was x0, y0, z0, what was this vector r, and what was the angle phi and theta. All right. Okay. So let's do that. So this is the original camera. I mean, my assumption that the camera is in the canonical view. There is some gimbal to that camera. The camera, when it rotates, will actually, when you physically rotate the camera will actually rotate about this gimbal. It's the same as when you fix a camera on a tripod. You can pan and tilt the camera, but it will not, that pan and tilt rotation will not happen about the camera center. It will actually happen about the gimbal of the tripod. Okay, so first thing I do is, I'm trying to get it to where it is in the world. So the first thing I have to do is I have to get the gimbal to the origin, so that I can actually apply a rotation to it. The mathematical equivalent of the actual physical rotation it is undergoing, right? So that's the translation, and this is that translation matrix. I'm calling it R1, R2, R3. Okay, this is that small vector between the gimbal and the actual camera center, the actual camera pinhole. Agreed? So far so good? Okay, so that's where I moved the camera. Then I actually rotated it by 2 rotations to get it into the orientation which it actually is in the world. Okay, so those 2 rotations I'm writing as a rotation about about x-axis by phi, followed by a rotation about z-axis by theta. Now this depends on how I'm measuring those rotations. So when you are doing that physical system, you will measure some rotations, and let's say you are rotating about y or z, you will use the appropriate matrices here. But you will need 2 because there are actually 2 angles of rotation that it is undergoing. Now after that, what happens, now the camera is in the correct orientation the way you see it in the world. I just have to move it to wherever it is in the world. So that's like a translation, x0, y0, z0. So that's the translation matrix here. Okay. Now this whole thing, remember I'm writing it backwards because the transformation that I apply first is on the right side, then the next one is to its left and to its left. So this whole 4 matrix transformation is what is taking my camera from the origin, from the canonical view to where it actually is. What do I need to do now? I need to invert it, right? Because that's how we did it. The action which will happen on the world point will be the inverse of this transformation. So I can just take this and do the inverse of these matrices. What do I need to do next? To complete my camera model. This is just a rigid body transform so far. Yeah, so the camera matrix itself, right? These transformations are just rigid body transformations on the 3D world so far. There is no camera matrix involved, so I'll just multiply it with the camera matrix. Notice each of these transformations I wrote as 4x4 matrices. The camera matrix cannot be 4x4. It's a 3x3 matrix because there's a collapse of one dimension involved in a camera. Okay, so this is that whole camera model. Now I can simplify it by saying this inverse. So A B inverse is B inverse A inverse. So that means all these matrices will invert and their order will also shift. So that's why this R matrix came here with minus R, and then I have this. Notice that the minus sign phi here became minus sign phi here because that's the inverse, and then this minus sign shifted here and that's the theta, and then this x0 y0 matrix came here. So that's my whole camera model for this pan and tilt camera. Okay. Now, if you have, let's say, a camera mounted on an aircraft, okay, then you have a lot of things to do because let's say the camera is in the belly of the aircraft and it can actually pan and tilt. Okay, but the aircraft itself can roll, pitch, and yaw. So you'll actually have 5 rotation matrices being multiplied by each other. Okay. So whatever your situation is, you can figure out the rotation and the translation that is appropriate for that situation. One more comment here. If you compare numbers here, these two are rotations. Okay. If your camera is far away from, let's say, this world plane, and it even rotates a little bit, there will be a lot of motion in pixels for a particular world feature. Okay, so small rotations cannot be ignored. Okay, but if your camera is here versus a translation of, let's say, 1 centimeter here, and the world is far away, the image points will be approximately at the same place, right? So when you are setting up a camera model, small translations can be ignored often, but small rotations cannot be. Okay. Now, if you notice, this R1, R2, R3 typically will be a pretty small translation compared to, let's say, x0, y0, z0, which might be a very large translation. Okay. So typically this matrix may be ignored compared to this, but small rotations you can't ignore them safely. Okay. So think about the aircraft example that I just said. The aircraft rotates about its center of mass. Okay. But the camera is in the belly, so the camera rotates about its own gimbal. And there might be, let's say, 2 meters distance between them. Okay? So you will need that 2 meter translation inserted somewhere at the appropriate place. But the aircraft is flying at 1,000 feet, so that 2 meter is not going to matter much. And surely, even if that 2 meter matters, for the camera, the offset from the gimbal to the center of the film for the case of an aircraft will not matter at all, right? Because that's really a few centimeters. So those types of small translations you can ignore. Okay, this camera model that I described to you just now, if I write it, this I showed you before also when I was motivating projective mathematics. If I write it in inhomogeneous form, it comes unwieldy and kind of difficult to understand, like this. But if you write it in matrix form, you exactly know what each matrix is doing. It's nice and simple, the way we wrote it in the last slide. And this is a camera model applicable in many situations. For example, this is a typical surveillance camera which can pan and tilt. Yeah. No, you can't ignore it at all. Think about first, let me give you a physical understanding, right? So think about the camera here and the camera, and this camera is, let's say, really far away on an aircraft maybe, and then it's rotated by 2 degrees. How much distance in the world that can cover? That will be a lot, which means the feature that maps at this pixel will be completely different. You were looking at this building versus that building just by a 2 degree rotation. And then you can do the same thing and figure out, because this is a vector, it's actually a ratio of x, y. I mean, the numbers are between 0 and 1, but what those numbers do is they change the ratio between x and y coordinates, because one of them multiplies by x and the other multiplies by y. So when they multiply with x and y, they are multiplicative, they are not additive. That's really the reason. The translations are additive components to x and y. So if x and y are very large and the translation components are very small, they don't really matter. But these are not additions, these are multiplications. And so even small multiplications change your number by a large amount, right? Okay, so the pinhole camera in the general view, this is my canonical view. Okay, now I wrote it correctly, mx, my, f, x0, y0, so it's in pixel coordinates here. This transform R pipe T is really identity right now. This is the extrinsic matrix, this is the intrinsic matrix, that's the world point, and this is the image point. The image point will be in homogeneous coordinates. If you want to plot it, you will have to convert it into non-homogeneous coordinates. Don't forget to do that. Okay, but that's where the actual division will happen, which is necessary part of the camera model. Now the surveillance camera that I just showed you is this with I ignored that R matrix, so it's this model which I wrote on the previous slide. Okay, now you can kind of compare them, right? So this is the translation which was identity here, and it's non-identity here. Okay, this is the translation in the world by minus x0, y0, z0, which is the inverse of the camera center. Okay, this here is rotation, which was also identity in the canonical view, but it's no longer identity. And it can be a combination of many rotation matrices, or it could be in that form of axis versus axis and angle rotation. It's really some orthonormal matrix here. Okay, and then this is the actual perspective transform. We also call it perspective transform. Don't confuse that with projective, which is a 2D to 2D transform. This is a 3D to 2D transform, or we call it the camera intrinsic matrix. Okay, the camera model really. Okay, so the pattern is the same. It's just that I had identity transforms here, and now I have non-identity transforms if I'm not in the canonical view. All right. Okay, so summary of we call this camera perspective camera, which is also the pinhole camera. That's why we call it perspective transform, because we use the English word perspective to see. I mean, you will see that lines are converging, things far away are smaller. That's the characteristic of a perspective transform. Okay, so I can write it compactly as x is equal to k r pi minus rc. Sometimes I'm using tilde here just to show that this is a 3 vector, not a 4 vector, even though it's a 3D world point, but I'm writing it as a 3 vector because the whole matrix is 3 by 4. Okay, and then I have a cap x here. This is the world point in P3, so it's a 4 vector. This is a 3 by 4 matrix of external camera parameters. We call them extrinsic parameters. This is the 3 by 3 matrix of internal camera parameters. We call them intrinsic parameters. Okay. External parameters will change if the camera moves. Intrinsic parameters will not change if the camera moves. But if you zoom your camera, for example, you have a zoom button on your camera, then the intrinsic parameters change, because zoom really is a change of focal length. Is that comment clear? That zoom really is a change of focal length, right? So, so intrinsic parameters will not merely change by a rigid body transform of the camera in the 3D world. Okay. So this K is really MXF, MYF, X0, Y0 arranged like this, where X0 is MXPX and Y0 is MYPY, where PX and PY is the principal point where the axis is cutting the film. And then this is the image point, which is a 3 vector in P2. Okay, so that's like one slide summary of the camera model. Any questions? Okay, so what I'm going to do next, which is very important related to the homework that I just posted, because you are actually supposed to simulate these scenarios in the homework. I'm going to show you 2 special cases of this camera model. Two specific cases, special cases of this camera model, which are very, very important in computer vision for a lot of imaging scenarios. Okay, so the first special case, and you have to actually implement both these cases in your homework, which I just posted. Okay, so the first special case is a perspective camera or a pinhole camera. I can use those terms interchangeably. A perspective camera looking at a plane. Okay, a typical scenario is like this. You have the surveillance camera looking at this parking lot. Even though the parking lot is not strictly planar, because these cars have a height of maybe about 1.5 or 2 meters. Okay, well, less than 2 meters maybe. So these cars have a height. So it's, and there are some of these trees here and maybe some light poles. So it's not a strictly planar structure. Okay. But it's approximately planar compared to how far away the camera is and the focal length of the camera. Okay, so the focal length of the camera is much smaller than the distance to this world plane, and so these structures will appear to me approximately planar. That's the claim that we have. Okay, so we often use this approximation even though it's not strictly true in certain cases. Okay, but I'll make this strict assumption when I'm doing the derivation. So the special case is that the camera is looking at a plane, and this scenario occurs frequently in imaging applications. Okay, so it's a pinhole camera, a perspective camera watching a plane. Okay, now what happens in this case? There will be a simplification that I can do on the camera model, and let's look at that. It's a very interesting simplification. So without loss of generality, I can assume that that plane has the equation z is equal to 0. Yani it is really the xy plane. Why do I say without loss of generality? Because where I fix my world axis when I'm building the camera model is really my choice. I explained this last time. There is no inherent axis there. I can choose it based on the problem according to my convenience. Okay, so I said, so here for my convenience, I'm saying the plane that I'm looking at, I will call it the xy plane. The x and y axis of the world lie on that plane somewhere. Somewhere there is an origin. So really the equation of that plane is z is equal to 0. Agreed? And this is not a restriction, because any scenario that you give me, I can choose my axis according to my convenience. So I find this convenient in this case. Okay, so so if z is equal to 0, then what does that really mean? This is my camera model. Okay, but in this particular special case, this coordinate here z will always be 0. It will never be anything other than 0. Agreed? What does that really mean? That means that this third column of R pipe T does not really matter, because this third column is always going to get multiplied by that 0 when I do the multiplication. Agreed? Okay, so what I can do is I can drop this column and drop this coordinate if I want to, because they are not playing any role. They are only going to contribute a 0 to my solution. Okay, so I can rewrite the system as well. This will become a 3 by 3 matrix. This will become a 3 by 1 vector x by 1, and this is already a 3 by 3 matrix. So a 3 by 3 matrix times a 3 by 3 matrix is another 3 by 3 matrix, which I'm writing as A1, A2, A3, A4, A5, A6, A7, A8, A9. Sorry, ऊंचा बोलने में, I can't hear you. I'm saying, yeah, okay. I'm saying because the world is a plane, yani all 3D points will lie on a plane, and I'm assuming that plane. I can assume that plane to be the xy plane. So which means z is equal to z will always be 0. If z is always 0, how does this vector multiply? Well, this 0 will get multiplied by this column. So this column really does not matter anymore. So I dropped this column and I dropped this coordinate and rewrote the system. And now what I'm left with here is a 3 by 3 matrix. This is also a 3 by 3 matrix. Those two multiplied is another 3 by 3 matrix, which I wrote in general form here. Agreed? Everyone follows that? Okay, so what does this look like? Affine transform? Homography. It's not an affine transform. Affine would have been if I only had A1 through A6 and the last row was 0, 0, 1. This is a homography. In fact, notice that this is a P2 vector now. It's those points on a plane. This is also a P2 vector, and this is a matrix linking those P2 vectors together with a 3 by 3 transform, which means there exists a homography between all these points in the world, which are now restricted on the plane. There exists a homography between all these points in the world and where I see them in the camera. It's now a 2D to 2D transform rather than a 3D to 2D transform, which is also interesting because homography is invertible. So in this case, actually, I can invert my image points into the world points also. How come, physically speaking, well, mathematically speaking, because homographies are invertible, by definition, homographies are invertible. But how come I can do this? Just a second, I'm going to lose power, I think. So how come it is invertible? Think of a point in an image. Previously, it was not invertible because when I want to back project this point into the world, I get a ray, and all points on that ray actually map to the same physical point. But now, since the world is planar, I can intersect that ray with the world, and I'll get actually a physical intersection. Okay, so that makes sense that it is planar. Sorry, we don't have printing of here. Oh, okay, got it. All right. So what's the conclusion here? 3D points, if they are lying on a plane, are related to the image points by a homography. And now it does not matter what the orientation of that plane is, because I can always assume that to be the xy plane by fixing my axis. So my proof holds, actually, even if it was not the xy plane, the proof is still valid. Okay? All right. So now, since I know that the world points in this case, which are on a plane, let's say on this table here, are related to the image points here by a homography. Now let's consider relationship not between one image and this world plane, but actually two images of this world plane taken by a pinhole camera, but the world is still planar. Okay. Now in that case, this is that plane, and there are some points on it. Let's call that plane xy. Z is equal to 0. And then I have two cameras that are imaging this plane. So I've already established that this transformation from the world to the camera is a homography. Let me call that H1. And then there is another homography, H2, that relates it to the second camera. Okay? But homographies, we know, form a group. So, which means they are invertible, and that they are closed. Okay? Which means that there will be a homography H1 inverse H2 between the two camera images. Agreed? Because homographies are invertible, I know this relation. The green points here on the world are related to this camera by h1. Because homographies are invertible, that means the camera points here will be related to these green points by inverse of h1. Okay, and then these points are actually related to the second camera by h2. So which means these points are related to these points by inverse of h1 times h2 in the opposite order. h2 times inverse of h1, because I'll first apply inverse of h1 and then h2, which means that any two images, inverse of h1, h2, these are both group operations. So, and there is group closure involved here. So, which means inverse of h1 times h2 will also be a homography. Which means any two images of a planar world by a pinhole camera are related to each other, image to image, by a homography. Okay, this is the key fact that you use when you make a panorama from, let's say there is an aerial video of shot from an aircraft off a ground, and you can stitch it into a larger panorama. Okay, so you can actually just find the homography between the camera images. So recall this figure. I showed you this before when we were talking about homographies. I said what I've done is I've taken a grid here and I've just projectively distorted it. I've distorted it by a homography into these images. But they do look like tilted planes. And now we realize that that's not a surprise, because images of a plane are related by a homography anyways through their camera model. Okay, so now we understand this fact which we were unable to discuss before. Okay, this fact is used a lot in this problem of rectification, which you also had to look at in your homework. Okay, the perspective image of a plane, which means the pinhole camera image of a plane, can be transformed into, because all images of that plane are related by a homography, there's one special image which is from here. So that will also be related by a homography to whatever image I took, that frontoparallel image. Okay, what is the definition of frontoparallel? The optical axis of the camera is the same as the ground normal, the plane normal. Okay, the plane normal and the optical axis coincide. So that's a frontoparallel image. Okay, in fact, it's not just one image, because any rotation of that like this will also be a rectified image. But that's the definition of a rectified image. I'm not looking at the plane like this, I'm looking at it like this. Okay, so here's an example. This is a drone image on my my university where I work in Makkah Mukarramah. So we are flying a drone. The drone has a camera. You can see that the camera is at an angle. How do you know it's at an angle? Well, parallel lines are converging. If I was looking at it from a top, like map type of view, then on this plane, parallel lines would not be converging. Okay, so what I can do is, I have only one image, but I know that there must exist another image which was actually like the top view of this, and I don't know that image, but I know that that image must be related to this image by a homography, and then I can go and find some corresponding points and try to find that homography. How do I find corresponding points? Well, actually, doing that rectification, there are many different methods to do it. But one way could be that, okay, I take this image and I go to Google Maps or Google Earth image, which is like a satellite image from the top, and then I mark some corresponding points. Like I see same features here, this tree and the corner of this building, and I mark some features, and then I find that homography of how this image would look like when I was looking at it from the top. So in this case, that's what I did. This is a satellite image I took from Google of the same location, and then I can mark some corresponding points. For example, this screen here, the base of this screen, you shouldn't mark the top of the screen because that's actually way off from the plane, and so it will distort your homography. But if I take the base of the screen, which is actually right here, you can tell that by the shadow, and then you can find the corner of this building, which is like here. Okay, and so you can find, let's say, the corner of this shade, which is this one. So you can find some corresponding points, and if you do that, then you can figure out the transformation H between this source image and the satellite image. And once you find that transformation, like you did in your homework, right, by least square or DLT or some method, once you find that transformation, you can actually apply that to this image that you had, and this is what you get. Does this make sense? I mean, does it look like a rectified image? What should you be looking for? I mean, it's like a weird distorted type of image, right? It's not making sense. But what should you be looking for? You should be looking for that those lines which were clearly parallel in the world but non-parallel in the image have now become parallel. In fact, if you wanted to check how good your rectification is, you should check how good these lines are in their parallelity. Because in the rectified view, they should be parallel. Parallel lines on this plane should now be parallel. Now, but also notice, let's say these two lines were parallel, right? The two edges of the screen, they are parallel in the world, and they are no longer parallel here. Well, because they are not on that plane that I was rectifying. Okay. Similarly, the buildings, they appeared, or these light poles here. I mean, these poles. Notice how they appear. They appear like long, dense, stretched, and so on, in a kind of crazy way because they are not on that plane. So what was rectified was that plane. The important thing here is look at, for example, these lane markers. If you were doing a self-driving car type of application, look at these lane markers. The lane markers now are equal length, whereas here they were in image coordinates, they were not at all equal length. They were getting smaller and smaller as you go along the picture, right? Because this was the distortion of the perspective transform. Things get smaller as they move further away from the camera. We understand that. But since I have rectified that plane, they are now equal lengths, which means maybe I can measure one of these markers in the world. Let's say it's 3 meters. Okay. So which means now I can make physical world measurements on this image, which was not possible for me to do here because these pixel dimensions were getting distorted as I went further away, which means a lot of very important things. I can measure speed of these cars, for example, okay, in the rectified view, whereas I couldn't have done that in that view, right? Yeah. No. If H was the transformation from this to this, then applying. Okay, let me see. No, it is H. So when I apply H on this image, it should become like this image, which is what this is. This is like this image now. Okay. It depends on which direction you define your transform to be. Because the transform is invertible, you could define it either way. So here's an example. This is the original video. This is the rectified video. In the rectified video, you see that we are putting speed marker on every vehicle because we can do that in the rectified video. Every frame is rectified, so the whole video is rectified. Okay, so I'm putting a speed marker there. And now, because I can measure speed in this view, I can actually measure speed in this view. So I'm doing a speed marker here. And what I show to my client, let's say, will only be this video. I'll just hide that because they're not interested in that. Okay, so I'll say, oh yes, I can measure speed of these cars, which I can only do because I was able to find the rectifying transform. Okay. One interesting thing that you might note here, I have cut this view from here. Even though I see certain things here like far away, like that bridge maybe there, but I've like cut that out. I've cropped this image beyond what the extents of this image is. Why have I done that? It's not accidental that I just cut it arbitrarily. There is a reason for that. Yeah. I have too few pixels. Yes, that's kind of right, but yeah. Okay, so yeah, there is a horizon somewhere here. Horizon is where these parallel lines will meet, so it's like somewhere here. But so what? What's the problem with horizon? There will be no cars beyond the horizon. Yeah, that's true. They will like fall off. There's this group of people who think in the flat earth theory. They have like they resist this idea that the earth is not flat, and so those guys would think, oh, the car will fall after that, right? It's just very far away. No, I mean, kind of you are both right, but the more precise reason here is the horizon is actually at infinity, right? We see it as a finite line in the image because of the perspective transform, but physically the horizon is at infinity. Uh, so when I rectified the view, because in this rectified view, the foreshortening distortion, the distortion of things get smaller as they go further away, has been corrected now on this plane, right? For this plane. So which means the line at infinity of this plane now actually is at infinity, right? Which means that to be able to draw the horizon in the rectified view, I would need an infinitely large image. And even if I approximated infinity by a very large number, that means I'll just be spending a lot of memory to store that image. Okay, and even if I say, okay, no problem, I'll spend a lot of memory to store that image, the point is I will not get any benefit, because like you said, pixels are getting smaller there in the actual image. So your information is being reduced of what you get from a unit in the world. So you will have a lot of pixels with really no information being added for you. In fact, think about it like this. Every pixel here stretches when it comes here. It scales, distorts when it comes here. The pixels which are close to the edge of the camera, which means they're closer to the camera in the physical world, stretch by a certain amount. The pixels which are further away stretch by more, because they have to cover more ground now to make equal lengths. The pixels which are further away than that stretch more, because pixels are discrete entities, right? So they keep stretching more. The pixels which are close to the horizon will stretch very, very large, to the extent that the pixels that are on the horizon will actually have to be stretched infinitely for them to give you a sense of physical depth. And it's one pixel that you are stretching so large, it doesn't have much information in it. You are just wasting that information. So when you are creating a rectifying view where the horizon is going to be visible in the original picture, you have to crop it at some reasonable location. So I could say, I could do a pixel to meters mapping, and I would say wherever one pixel covers more than, let's say, 20 meters, I will end there and no more, because it's really not very useful for me. By the way, this stretching you can actually see if you look at this video carefully, right? So take a car from here and start following it. You will notice that the car like elongates as it goes towards the edge of the image. Okay? It's like a small car when it's at the bottom of the image. As it goes forward and forward, it kind of elongates. Why? Sorry? Yeah, but yes, but still I found a transformation which is like perfect mathematics, right? So why is this stretching happening? I mean, my previous slide where I did the transform, convincing you that image 1 and image 2 are related by homography, that did not say that it would be a homography, but with some stretching. Exactly, that's the point. The car is actually not perfectly on the plane. It's not an object of that plane. It's actually coming out of that plane. Okay. Now that coming out is not describable by my transform that I did so far, because my transform was for the points on the plane. Now this, think of it like a window, the back of the car and so on. Think of it like a window. When I'm looking at it like this, I'm assuming that it's on the plane. So it kind of falls like a shadow on the plane. Now, as it goes further away, that falling covers more distance on the ground, because it's more closer to your horizontal horizon, right? And so the cars actually, because they are non-planar objects, they actually just keep stretching as I go further away, which is an inaccuracy. Okay. What I'm doing here, by the way, if you notice carefully in this demo, I'm actually measuring speed from the point which is at the bottom of the car, because that point is actually close to the plane. And so these every car here is a dot on it, right? And notice that that dot remains on the back side of the car, because that's what I use. Because if I was using a point on the front of the car as the point of measuring speed, that point will actually undergo more distortion, or on the top of the car, so it will actually undergo more distortion and my speed measurement would be more inaccurate. Okay, so the transformation holds perfectly if your data is perfectly planar, then there is no problem. If I were distorting these lines, for example, the lane markers, they don't stretch unreasonably in the rectified view. They remain the same. But the car is an object which is outside of that plane, and that's why it's not following that transformation perfectly. All right. So once you rectify, you can do other things with it. Here's another kind of scenario. So this is kind of like the same image that I was showing. One camera. This is another camera which is further along on the road, and this is another camera which is further along on the road. These three cameras are covering a stretch of the road which I've kind of approximately marked here. And really what I can do is I can rectify each one of those images. So this is the red part is this image rectified, and the yellow part is this image rectified, and the green part is this image rectified. And you notice that there's some overlap between them in this space because these cameras were one after the other along the road and there was some overlap in them. And so what that gives me is like kind of like one long image rather than these small images. I can fuse my information together because once I rectify, they are in the same coordinate space. They are in the coordinate space of that satellite image, and so they can overlap. I can't overlap them here, right? Because each one of them has its own perspective transform. But once I rectify, they're all on that plane, and so I can stitch them together if I want to, which is how you make a panorama. So this is like a merged view of the road that I get from my three cameras together. Okay, and now I can this is another demo we made. So so the car will come here, and so I'm plotting it on a map because I can track it. I can plot it on a map, and this plotting on the map, now it comes here, and then you will see it here. Those cameras have individual views, but this view is kind of like their fused view together. So you can take all your cameras in the city, and if they were overlapping cameras or even non-overlapping cameras, you can kind of put them in one kind of view space, which is very useful in certain applications. So for example, let's say you were interested in finding whether somebody is driving dangerously by zigzagging along the road. Now that zigzag maneuver may not be fully seen in one camera because it happens over more than one camera. Okay, but in this view, once you have converted them into like standardized rectified coordinates, you can just look at that curve and see how that's going and have some rules on that curve. Okay, so it's like a extended virtual camera that you built just by homography transforms. Okay, all right, good. So any questions? Here's one other example. Let me show you this, again from the work we are doing in Saudi Arabia. So we build using deep learning, which is something we'll cover later in the course, inshallah. Using deep learning, we build a person detector so that in an intensely crowded image like this, if you look closely, there is like a red dot on the head of each person. Okay, can you see that? So there are a bunch of red dots in the scene. Those are actually dots put by our image recognition code, which is based on deep learning, saying this looks like a person, this looks like a person, this looks like a person. Okay, we'll cover techniques like this, inshallah, in the second half of the course. Okay, so but once I have done that, I actually wanted to convert it into density scale, which is on persons per meter square. Okay, and to be able to do that, I have to do rectification because here my image measurements are getting smaller as I move further away from the camera. So what we did is we rectified this image, and in the rectified image we then marked what is 1 meter by 1 meter, so 1 meter square, and then in each of those 1 meter squares we counted how many people there were and color coded that square like that, and then we unrectified it back again by H inverse of that transform. So these squares that you see here are all physically 1 meter by 1 meter. Okay, but in the image space, you notice that these are bigger and those are smaller, which is what you would expect. So rectification is important because now it allows you to do physical world measurements because you undo the perspective distortion, the non-parallelity type of distortion, you undo it, map it to world coordinates, you can do physical world measurement. This is another example of physical world measurement done on meters, square meters. and then you can display that on your image by the inverse transform. Okay, all right. Let me talk about, so that was one special case. The special case of camera that I wanted to talk about was perspective camera, pinhole camera, looking at a plane. And all images of that camera are now related to each other by a homography, a 2D homography, P2 to P2 mapping. Yes. No. Uh, okay, so self-driving cars have multiple types of sensors in them. At least the versions that are there so far, they have multiple types of sensors in them. For example, a lidar, which is a laser-based device to find the point cloud in front of it, so that it can measure how far away objects are. It has radars also on it, but it also has visual range cameras. Okay, and the purpose of having these multiple sensors is redundancy. So you can fuse information from multiple sensors so that if one of them fails, the other should not fail. So, for example, you know about the recent crash that happened for the Uber test vehicle. Somebody died in Arizona. A lady died in that crash. If you look at the videos were released by the Department of Transport there. If you look at the video, yes, it's actually very difficult to pick up that lady just before the crash because it was dark there. The headlights did not pick her up. She was completely in a dark shadow at night, and then she came in front of the car at a very late stage. But the radar should have picked it up, and the lidar should have picked it up. That's the reason for having redundancy, that if one modality fails, the other one does not. Now your question of what is that camera doing? Well, a lot of different things. So for example, one thing is recognition. So it's a pixel-wise recognition of where is the road, which pixels belong to the road, which pixels belong to trees, which pixels belong to road signs, which pixels belong to humans, which pixels belong to other cars, which pixels belong to bicycles. There are a bunch of categories that the camera is processing in real time to understand the scene around it. Okay, that's all recognition. That's the second half of this course, which we will do in the last 3 or 4 weeks. But the camera is also doing a bunch of other things. For example, when it finds the road pixels, it actually finds the horizon line, and from that it rectifies so that it can convert some of the things into distances and figure out the lane markers and their dimensions so that it can path plan along that. So that all part is geometry, which we are discussing right now. Okay. If you follow this company, which is called Mobileye, Mobileye was like about a year ago, I think they were acquired by Intel for about $5 billion. Mobileye is a manufacturer that makes in-vehicle cameras. It's a pure camera device. There's no lidar or radar associated with it. In a lot of new cars, you have this feature of adaptive cruise control, where if you set your speed to 120, let's say, and the car is driving at 120, if there's a car in front of it, the cruise control will adaptively automatically slow down till that car moves away, and then it will go back to 120. Okay, and that's done purely in mobile. So most of these adaptive cruise controls in the new cars are actually Mobileye systems. They are bought. The car manufacturer purchases these from Mobileye. You can even now buy a device from Mobileye which installs in your car, even if your car doesn't have adaptive cruise control, and it will alert you if there is a vehicle too close to each other compared to your speed. Okay, and this is a small device. It's based purely on visual range processing on a camera and processing video from that. So now you are finding distances, you are finding where the lane markers are. It alerts you if you change a lane, for example, without using your indicator, okay, your turn signal. So, so all of that is being done in visual, and there is a lot of geometric processing that goes inside that. In fact, the CEO of Mobileye, the guy who made that company, the co-founder and CEO, was a top-notch geometric computer vision professor before he left academia and started his company. So we used to see him at conferences and so on, and he had a lot of research on 3D geometry, which is what has gone into that product. Okay, and it's a very successful product. They have shipped more than 5 million devices now, or even more than that, the world over in different cars. So it's a very popular and stable product. Okay, all right. So yes. Like what you see on the highways and so on. So far, typically those cameras are based on radar or lidar technology. There are 5 or 6 major vendors in the world. All of them are not offering a visual range camera so far. I have a startup which works on that. So we are trying to make speed cameras as well as other dangerous driving cameras based on visual range only. So far, this product is not on the market. By the way, Safe City is very interesting. They have a bunch of different cameras, and they do a bunch of different things. So we will, if you guys are interested, we are in touch with Safe City authorities here. So if you guys are interested, we can maybe on some weekend or something, we can arrange a visit there. Because the setup and the type of cameras they're using and the different things that they do is actually quite interesting, and it's a big achievement in terms of tech and implementation that they have done. Okay, so I don't know if you guys are interested or not, but they are open. They allow university visits, and I'm in touch with their CEO. There are many different types of cameras they have deployed. It's not just one type. So there are ALPR cameras which capture license plates. These are the ones you see on the boom with the lights on them, 5 or 6 cameras in a row. They have just surveillance cameras, which are the dome type, like this one that you see on the roads. There are a bunch of different deployments that they are doing. They have cameras that are installed specifically to do face recognition, for example. So they have a database of suspicious faces, mashkook afraad, and then they are just scanning all over the city to find them, which is a bit scary. Yeah. Really, the viewpoint and the zoom level and the number of pixels you have, not much more than that. So it's the difference is in the deployment and the configuration mostly, rather than the actual physical camera. Okay, so the second scenario that I wanted to talk about, the second special case is that in the previous case, I did not put any restriction on the camera. The camera could be anywhere, but I put a restriction on the world. The world is going to be planar. Now, I'm not going to put any restriction on the world. The world can be planar or non-planar or 3D or however. I mean, it's a 3D world, right? But I put a restriction on the camera. The camera is only going to rotate about its imaging center, about its pinhole. Okay, so this is like a panning camera that you might have in a security system. Okay, so now we consider the case. So like this camera, for example, it does not perfectly rotate about its imaging center, because the imaging center is at the center of the lens. It really rotates about this gimbal. But like I said, if the world is far away, if this is on a high pole, that difference is going to be minor, and so I can assume that it really rotates about its imaging center. Okay, so the case that I'm considering now is the case of a camera that does not translate, there is an extra S here, but only rotates about its optical center. Okay, let's see what the camera model for that looks like. And this is also a scenario that occurs very frequently in imaging applications. Okay, in fact, this is the real scenario that you are doing when on your cell phone you are making a panorama. Okay, so you are not moving, you are not translating, you are at kind of one place, but you are just rotating your camera. Okay, approximately about its optical center. Okay, so this is a case of pure rotation, because I'm saying there is no translation involved. So let me say that x and x prime are the images of point x, because there is a world point cap x, as I first take one picture, then I rotate the camera and take another picture. So the first picture are the points x, and the second picture are the points x prime, which are before and after the rotation of r of the camera respectively. Okay, so the camera undergoes a rotation r, but it does not undergo any translation. Now, if that's the case, well, before rotation, my model is going to be this. I can assume that before rotation, I was in the canonical view. Without any loss of generality, I can make that assumption. So small x is k, and then I used I pipe 0 because there is no rotation or translation so far into x. Okay, so I assume that that's canonical view. But what about x prime? The x prime is going to be this equation, k r pipe 0. That's the difference. This 0 has not changed because I have not translated, only that I have introduced some rotation r in the camera. So that's x prime. Everything else remains the same. Okay. Now what I can do is I can try to relate both of these images together, the x and x prime coordinates. Let's try to do that. So k r pipe 0x, I can take r common. So that's k r. So that was k r pipe 0. Now it is k r I pipe 0 because I took r common. And then once I took r common, I just multiplied in here a k inverse k. Since k is an invertible matrix, it's an invertible 3 by 3 matrix, k inverse k should be identity, so I've really not changed anything in the equation. It's just for the matter of proof that I introduced that in the middle. Okay, and then the rest is I pipe 0. But now notice, what is this thing? That's really just in the form of x, small x, so which means x prime is equal to k r k inverse x. Okay, and what's the dimension of k? 3 by 3, and what's the dimension of this r? Look from here, 3 by 3. Okay, and what's the dimension of k inverse? If k is 3 by 3, k inverse is also 3 by 3. So 3 by 3 matrices multiplied together will also give me another 3 by 3 matrix. So I have a 3 by 3 matrix relating two P2 entities. So it is a homography. Okay, so which means that x prime is k r k inverse x, or I can just say x prime is some hx where h is equal to k r k inverse. Okay, this type of homography, this special type of homography, which is a k r k inverse homography, is actually called a conjugate rotation homography. Okay, and in fact, conjugate rotation does not have full 8 degrees of freedom of a homography, because there are 3 degrees of freedom in R, and there are 1, 2, 3, 4. Well, it depends on how you set up your model. If you are setting up in real world coordinates, there are only 3 degrees of freedom in K. So that's 6 rather than 8. So it's a homography, but it's some sort of restrictive homography, which is a homography that generates out of pure rotation of the camera. So homographies are incredibly important because they're cropping up in all unexpected places. Right? But this is really what happens when you make a panorama. When you are making a panorama, you do not compute, at least the way it's done in your cell phones, you do not compute the 3D structure of the world and try to stitch things together. No, not at all, because you realize that the user is mostly going to rotate the camera. So I can just relate those images by a homography by 2D to 2D. And you try to estimate those homographies as you are moving your camera. The algorithm tries to estimate those homographies and stitch all of them back together into one large image. Okay. Here, this is not a very clear figure, but I just still thought it's a good illustration, so I want you to see this. There's an image A, B, and C. Between A and B, you notice that things have moved, but between A and B, we have done a pure rotation, while between A and C, we have done a rotation as well as translation. Okay. Now, how can you tell? So notice that when you do a translation and a rotation, there is a parallax change in the image. By parallax change, I mean things at different depths move across each other. Okay, so notice, for example, the tip of this was on that black portion of the poster, but now it has translated from that. Why? Because this vase was closer to you than that poster. When you translated, the closer things moved more than the far away things. Okay, we are used to this phenomena. When we are going in a car, the trees look like they are moving backwards compared to the far away fields, let's say. Okay, so that's parallax. So you can see that, for example, look at look at this cup, for example. So the cup is now here, it's joined to that cartoon. What is it? It's a cat, I think. So the cup and the cat are like joined to each other, but here they are not. Okay, but if you look at the pure rotation part, there is no change in parallax. The tip of the vase is exactly at the same position as here, even though things have moved, right? The posters are not at the same location. Things have moved because there is a rotation, but there is no change in parallax. The cup is still joined to the cat, and so on. Okay, and that's not a surprise, because when you did a pure rotation, the image actually distorted just by a homography, and homography is not going to. Homography is like a stretching of the image. It's not going to change it. It's not going to change your parallax. But when you actually translate, then parallax changes. Okay, if I put my finger here and I translate, now there is another person in its line rather than here. Okay, but if I was purely rotating, that will not happen. It will be related only by a homography. Okay. All right. So the relative motion of objects in two images which are at different distances in the world is termed as parallax. A homography will not generate any parallax. Hence, pure rotation camera does not generate a parallax. Okay. So the image taken by a purely rotating camera, you can think of it as just like a wider, bigger image. Okay. Which is why you are able to make nice panoramas in that case. Okay, done. So we are done with camera models, at least this part of camera model. Okay, any questions? Yes. Okay, so sometimes you make a panorama and you end up with an imperfect panorama, and the reason for that is that what you were executing was not a pure rotation. You were also translating your camera. It wasn't purely rotating about its camera center, and then that results in some imperfection in the mapping, and then you see like a cut face or something like that. Yeah, that's also the case. If you were doing a pure rotation, but actually the persons were moving, then that doesn't map, because the world points themselves move. So in one image, this guy will be here. In the next image, this guy will be here, and then you will see maybe a double person in your panorama, or maybe a disappeared person in your panorama. Okay. All right. So let me then begin with this very important topic of calibration. So far, we have talked about camera models. This is like the summary slide of the camera model. Okay, I showed this to you before. I can write this as, well, ultimately K, R, pi, T, all of that together is a 3x4 matrix. Okay, so I can write it like this. I'm using P for perspective transform. Don't, by the way, confuse perspective with projective. Projective is a P2 to P2 or a P3 to P3 mapping, whereas perspective is a P3 to P2 mapping. So don't confuse the two terms together. Okay. So this is what the camera model is in general, right? Just in its absolute summarized form, it's like a 3x4 matrix. That's what I said last time. A camera is a 3x4 matrix. Okay. So the question becomes, I can write it as x is equal to px. The question becomes, it's a 3x4 matrix of rank 3. Well, because there are 3 independent rows. Okay. In fact, it has to be of rank 3 to make it a pinhole camera. If one of the rows was dependent on the other two, it would be a camera of some other type. It wouldn't exactly be a pinhole camera. There would be some problem with it. Okay. Which is also a camera. Actually, any 3x4 matrix is a camera, but those are cameras of other types that we have not studied yet. Okay. All right. So calibration is the process of how do I find these parameters? How do I find P1? I mean, you have a camera in your pocket and you took a picture. How do I know what are P1 through P11 to P34? How do I know what's the rotation of the camera? What's the translation of the camera? What's the focal length of the camera? What's MX? What's MY? What's the principal point? How do I figure those things out from the camera? Okay, so we say the process of doing that is calibration. And in fact, in calibration, the approach that we take is, so far we were saying, I know this matrix, I will multiply with this and I'll get this. The approach we take in calibration is, I don't know this matrix, but I know some corresponding points. I know that this world point mapped to this image point and this world point mapped to this image point. If I know a bunch of those, it's a linear system, I can solve for P's. Okay, so that's the straightforward way to talk about calibration. So if x, small x and cap x are known, then we can solve for the unknown parameters in P. Okay, okay, so let's look at that. This is your camera model. Okay, no issues with that. What I'm going to do is I'm going to convert it into inhomogeneous form. This vector is in homogeneous form. I'm converting it into inhomogeneous form, which means x will be h of x divided by h, right? And h of x is nothing but this dot product of this first row with this column. So it's p11x plus p12y plus p13z plus p14. And h is nothing but the dot product of this third row with this column, which is p31x plus p32y plus p33z plus p34. Okay, so I just divide those two. So that will be my x coordinate in the image, where the point xyz maps to. Agreed? And my y coordinate will be, so the dot product of the second row and the third row with the vector xyz. Okay, so I got that. So I'm just going to, the denominator is the same. I'm just going to multiply by that denominator and rearrange this. I get this for x. Okay, how come I get this for x? Just verify. p11x plus p12y plus p13z plus p14 minus p31xx, because it was on that side, I bring it here, so it's minus, right? And then p32y small x and p33z small x and p34x equal to 0. So it's just a rearrangement of this equation by getting rid of the denominator. And the second one is this. Okay. And what are the knowns and the unknowns here for the calibration problem? My cap x, cap y, cap z, I will assume that they are known. My small x, small y, I will assume that they are known. And my p's are all the unknowns that I will try to solve for. Okay, so these are the two equations. How many unknowns are there? There are really 12, because those were coming from the 3x4 matrix. So there are 12 unknowns here. Each corresponding world point and image point. Each correspondence between a world point and an image point actually yields two equations, which are these, right? So how many points do I need to constrain this? I need 6, right? So 6 correspondences are known. If you know the correspondence between 6 world points and their corresponding image points, subject to certain conditions, we'll talk about that. You can solve uniquely for P1 through P34. Let's do that. We'll do the simple least squares solution, even though in practice DLT is direct linear transform is much more popular. But I'll just do the least squares solution the way we have done this before. Okay, so I'll separate out the known and the unknown terms. So that actually comes out to be this. You can verify x1 times p11, which is this term, y1 times p12, z1 times p13 plus p14. And then in the first equation, you do not have p21, 22, 23, 24, so you put zeros there. Okay, and then you have with p31 you have minus xx, so that's coming here, and so on. Okay, so it's really the same two equations written in matrix form. Okay. Now, if you have n correspondences, you have n pairs of rows here. You need at least 6. You could have more than 6 and do a least square solution. Fine. So this is what your matrix would look like. These are the unknowns, and on the other side you have zeros. So in a sense, this system is slightly different from the system we did for affine or projective transform, because we didn't have zeros on the other side. But in this case, on the other side, you necessarily have zeros because all the p's were multiplying to some coordinate or the other. So you didn't get anything on the other side. Okay, so this is a system of the form A, P is equal to 0. And how can I solve it? So P is a null vector of A. Actually, by definition, this is what a null vector is. Okay, so AP is equal to 0 is a homogeneous system. This system, because it's a homogeneous system, it's rank efficient. My claim is that the rank of A has 12 columns. It is required that it has at least 12 rows, or maybe more if you have more correspondences. Okay, so the rank of A should have been 12. But since AP is equal to 0, from my model it's given me AP is equal to 0. That means the overall scale factor of P in the solution does not matter. If any P is a solution, twice P is also a solution, which means that the rank of A is going to be 1 less. The same way as we argued about rank before. So it's going to be 1 less because think of it like this. Because the scale factor of P does not matter, let me fix one of the P's, let's say the last one at 1. This, by the way, we don't do this in practice. I'm just giving it to you as a mathematical analogy to think about it. Because the scale factor does not matter, let me fix the last P as 1. If the last P is 1, then the one of the column does not have a P term in it. In fact, that column can be written as a linear combination of the other columns. Okay, it becomes an equation, something is equal to that column. So that column is really a linear combination of the other columns. And that's the argument for rank deficiency. Okay, because it's a homogeneous system, the scale of P doesn't matter, therefore A must be rank deficient. Okay, so the rank of A can at most be 11 and not really 12. If it was a system of form AX is equal to B, I wouldn't have imposed this rank deficiency. But it's a system of the form AX is equal to 0, so then it is necessarily rank deficient. Okay. So what's the solution to this? You already said that. I could just find the null vector of A. The null vector of A, the right null vector of A is P, which is the solution of AP is equal to 0. All right. How do I find this null vector? I could do SVD. So I could either do just null of A in MATLAB, or I could do SVD. I would do SVD of A. Why did I say C? SVD of A will be U S V transpose. And then I will take the column of V, or the row really of V transpose, which is the column of V, which corresponds to the singular value of 0 in the solution. Okay. In practice, because the points in A are coming by noisy measurements, they are not perfectly accurate points. You are measuring 3D world points, you are measuring image points. So in practice, actually, if you find the singular values of A, none of them comes out to be perfectly 0, because the data was not perfect which generated it. The correspondences were not perfect. There was some noise in them. Okay, so you don't get them to be perfectly 0. So what we do is we just see which one is smallest, and we say, well, that should have been really 0. So let me take that vector. It should be really close to the actual solution. So that's what we in practice do. If we use this method, well, really in practice we don't use this method. It's for the same reason as I talked about homography. It's more sensitive to noise because it's a least squares solution. So we prefer something like the direct linear transform. So summary: given a set of world points in 3D coordinates and their corresponding image points, we will solve the 3x4 matrix that relates them. This transforms the problem into a problem of the form AP is equal to 0, and I solve that by finding the null vector of A. A more robust solution, I'm just mentioning it here so that you know it's there. I'm not going to discuss it in the course, but a more robust solution is something which is called the direct linear transform. It's less sensitive to noise. It's more recommended that we use that solution even to find a homography or to find the least squared solution here in the case of camera calibration. Okay, so I'm going to stop here, but what we are going to do next time, inshallah, which is after Eid, is I got P, but how do I find K, R, principal point, focal length, T, camera center, C? How do I find those out of this matrix P? Okay, we'll talk about that problem next time, and then I'll show you an example in practice. Any questions? Yeah, okay. So the class will end here, which means I'll